Good evening. If you're in the class, please drop a reaction. If you're in the class, do drop a reaction. We are about starting. Drop a reaction. We are about starting. Drop a reaction. We are about starting if you're in the class. Anyone in the chat? Anyone in the class right now? Drop a reaction if you're in the chat. We are keep starting right about now. The live chat is open, so if you are on the call, just drop something in the live chat. Say I, say hello if you're in the call. If you're on this call, if you're on this live, please do well to drop a message in the live chat. Let me know that you are in the class, please. Anybody there? All right. So we are going to proceed. We're going to proceed. Hopeful, and I trust that others will join us even as the class goes on. All right. So I'll be dropping questions that we'll be answering today. Any question that we'll be answering, I'll be dropping it in the chat. Okay. So we'll just go through it together. Just check it out. Then I'll provide a solution on the board. Okay. So I'll be dropping the questions using a particular account. Okay. So I'm going to drop the questions there on the chat. Then we'll answer together. All right. So I would want everyone on the chat to drop a message. If you're on the chat, just drop a message to indicate that you are on the call. All right, I can see some. Okay, let's keep it coming. Let's keep it coming. All right, let's keep it coming. Let's keep it coming. Let's keep it coming. Drop those messages. Drop those messages. Let's keep it coming. Okay. All right, so let's quickly start. We have spent so much time already. So let's quickly start. All right. Good evening and welcome to Physics with Polamine and another evening of our physics clinic. We started last week and we're going to continue today. We started with the conversation on heat measurement and heat capacity, where we looked at specific heat capacity and the difference between specific heat capacity and heat capacity. As well, we also looked at heat and temperature, where I said that it is you cannot talk about heat without considering temperature. Same way you cannot talk about temperature without talking about heat. I highlighted that heat is a form of energy that can be transformed, or so that can be transferred from a hotter body to a colder body due to temperature difference. Okay, and temperature is just simply the degree of hotness or coolness of a body, or the average kinetic energy of the molecules that make up a body. That's what comprises temperature. So you cannot talk about this temperature without talking about heat, or rather talk about heat without talking about temperature. All right. Then we also saw that heat, the heat quantity a body can possess, or the heat a body loses per time, or a body gains per time, depends on three major things. Depends on three major things. So that the mass of the body, the specific heat capacity of the body, and the temperature difference that body will undergo when an amount of heat is supplied to it. All right. So we also considered some very basic questions and how the methods that we can use to measure heat. We looked at the electrical method and the method of mixture, where a body at higher temperature is brought in close proximity, is brought into a system where there's another body, but this time around at a lower temperature. We said that heat will be transferred from the outer body to the body at a lower temperature. That's how it flows basically. And because of this, there tends to be one body losing heat and another body gaining heat, basically. All right. So we solved some other questions. We solved some other questions, but today we'll continue with our conversation and also look at some other exam questions and try to provide solutions for them. Okay, so once again, you're welcome to Physics with Polamine today on our Physics Clinic series. All right, so if this is your first time, yeah, if this is your first time of being a part of this class, please do not forget, or if this is your first time visiting this channel, please just do well to press the subscribe button so that you won't miss out on any of our live classes or our video lessons here on this channel. All right, so press that subscribe button right now, and don't forget to like, comment. All right, and the live chat is currently on, so if you have a question, please do where to drop it in the live chat. Do where to drop it in the live chat. Any gray area that is not clear to you, do well to drop it in the live chat, and we'll be attending to all questions. All right. So I'll quickly clear the board now so that we can start. We have spent good amount of time from the time we are supposed to use. All right. So get ready. We kick start now. Okay, so if you are not yet on the chart, please let's get our notepads ready. Let's get our notepads ready, our calculators also. Let's get them ready. We're about to delve in proper. So let's get it ready. Let's get it ready. Let's get it ready. We're about to delve in proper. All right. So does anybody have a question from our last class? If you were in our last class, if you have a question from our last class, if you have a question, if you have a question from our last class, there's a question you encountered while you were going about your personal studies for the week, and you want to ask them, please do well to drop them now. We're about to start. We're about to start. If there's any question, please do well to drop. We're about to start. All right, so this is physics. This is a physics class. Just for the physics clinic. It's not really a topic. It's not really a subject. So just been trying to put it there as physics clinic. So we saw specific heat capacity last week. We said that specific heat capacity is the amount of heat energy that is required to raise the temperature of 1 kilogram mass of a body by 1 Kelvin or 1 degrees Celsius. and that is giving us the specific heat capacity. C is giving us the amount of heat required to raise the mass, 1 kilogram mass of a body by 1 Kelvin or 1 degree Celsius. Okay, and this formula takes its root in the heat quantity a body can possess, which is mc delta. I think I used theta last week. Mc delta theta, where h is my heat quantity, m is the mass of the body, c is the specific heat capacity of that particular material or that particular substance, while this delta theta is the amount of change that amount of change in the temperature of the body that resulted because of the application of heat. Okay, so this is a formula for heat quantity, and this C here is what we obtain here. If I make C the subject of the formula, it will be C equals H, okay, yes, joules. It will be C is equals H over M, then delta theta. Okay, so this is the formula for specific heat capacity. And we also saw that if this is the amount of heat that is required to raise the temperature of 1 kilogram mass of a substance by 1 Kelvin or 1 degree Celsius, what about a situation? What about a situation where I'm considering the heat required to raise the entire mass of that substance? That is what we now see when we talk about the heat capacity. We'll talk about the heat capacity of a body, the heat that is required to raise the entire mass of a substance by 1 Kelvin or 1 degree Celsius. And it is giving us Cp. Okay, that's the symbol we are going to adopt. Cp. Cp, and it says Cp is given to us as the product of the body's mass times its specific heat capacity. The product of a body's mass and its specific heat capacity will give me my heat capacity. Okay, so that's what we established in our last class. Specific heat capacity, the mass of the body times the specific heat capacity. All right, so let's quickly continue. We also saw some questions, some basic questions where we say if a body of mass, let's say a body of mass 0.5 kg, if it receives an amount of heat, if it receives an unknown amount of heat, let's call that unknown amount of heat H. Okay, and this amount of heat, unknown amount of heat that was applied, causes the body's temperature to increase from, let's say, an initial temperature theta 1, 25 degrees Celsius, to a final or new temperature of, let's say, 75 degrees Celsius. If this body has a specific heat capacity of, let's say, 4,200, let's assuming it is water. We are assuming it is water currently, all right? So what amount of heat was actually supplied? That unknown amount, okay? What amount? Let us quantify it. If the body is we are considering here is 0.5 kilogram mass of water, and it causes a raise in the temperature of the water from 25 degrees Celsius to 75 degrees Celsius. What will be that amount of heat? That amount of heat that was supplied, what would it be? All right, but so that amount of heat can be obtained from this formula we saw earlier, that H is equal to mc delta theta. If I am to open this, it will be mc, change in temperature, that is delta theta, will be final temperature minus the initial temperature. So I'll quickly slot in my values now. The heat quantity, the unknown heat that was supplied, is giving us the mass, which is 0.5, times 4,200. Then this into bracket the final temperature 75 minus the initial temperature 25, and this will go to 0.5 times 4,200 times 75 minus 25. 75 minus 25 will give 50. We gave 50. So I want you to punch your calculators if you have a calculator there, and let's get the value for 0.5 times 4,200 times 50. We have 1 minute to do that, please. If you've gotten your answers there, just type it in the chat. If you have gotten your answers, just type it in the chat. What's 0.5 times 4,200 times 50? 0.5 times 4,200 times 50. Type it in the live chat if you have gotten your answers. Let's go. 30 more seconds. 30 more seconds. 30 more seconds. If you've gotten your answers, type it in the chat. 0.5 times 4,200 times 4,200 times 50. All right, so our answer there will give us 105,000 joules. To give us 1,500 joules, this is equivalent to 105 kilojoules. This is equivalent to 105 kilojoules. So this is the amount of heat that will be applied on a body of 0.5 kilogram if that body's specific heat capacity is 4,200 and it causes a raise in the body's temperature from 25 degrees Celsius to 75 degrees Celsius. So this is the amount of heat that was supplied, 105,000 joules or 105 kilojoules. All right, so this is just a basic question under measurements of heat. Now, from our last class also, I think I mentioned that it being a form of energy, just like every other form of energy, it can neither be what created nor destroyed, but can be changed, can be transformed from one form to another. Electrical energy can be converted to mechanical energy. Mechanical energy can be converted to chemical energy. All right. So if that is the situation, it means that if a body loses its lost, if a body loses it in a particular environment, it means that every other object that is in close proximity with that particular object will gain that heat. Okay, so we say that heat lost is always equal to heat gained, especially in a conserved system, a system where there are no external forces. All right, heat loss is equal to what? Heat gain. So if I have a body, let's say a aluminium block, let's say I have aluminium block that is at a particular temperature, an aluminium block at 100 degrees Celsius, and then I dip my aluminium block into water, into a bowl of water contained in a bowl of water. All right, I dip this into water contained in a bowl. All right, so if I do this and my water is at a lower temperature of 25 degrees Celsius, now what I'm going to observe is that the aluminium block being at a higher temperature, it means it is hotter than this water at 25 degrees Celsius, we lose some part of its heat. To the water. So as it's losing that amount of heat, its temperature is dropping. So as its temperature is dropping, the water's temperature is increasing. Okay, because in this case now the aluminium block is the substance that is losing heat, while the water is the substance that is gaining that heat, that is receiving that particular amount of heat. So we observe a change, a reduction in the aluminium block temperature, while an increase in the water's temperature. All right. But then we will get to a particular point where both the aluminium block and the water will tend to be at the same temperature, what we usually call the equilibrium temperature. So it will end up that the final temperature of the aluminium block and the water will end up having a particular value. Okay, so the aluminium block and the water after some time will tend to be at the same temperature. They will tend to have the same temperature. That temperature is known as the equilibrium temperature, or we just usually call it the final temperature of the system, of the combination of the aluminium block and the water. Okay, that is the final temperature or the equilibrium temperature. Let me add that, or the equilibrium temperature, the temperature where the materials that make up that particular heat system, they are at the same temperature. Okay, so when the body loses heat, another body gains that particular amount of heat. Okay, so we are going to see a question as regards this. We are going to see a question as regards this, and if you have been following, please do well to indicate in the live chat that you are following. Indicate, drop a comment in the live chat that you are following. Or if there's something that is still not clear, you can also drop it in the live chat and I'm going to attend to it before we proceed. I'm waiting for your messages. I'm waiting for your messages. Let's drop those messages in the live chat. Let's go, let's go. Let's drop those messages in the live chat. Expecting your messages. And if you are following so far, please indicate if you are following so far. Drop a message that you're following. All right, so we are going to be seeing a question. I'm going to drop the question in the group. Okay, I'm going to drop the question right now in the comments. So from there, we'll be solving it directly on the board. There will be no need for me to solve it or write the question on the board. I'm just going to drop it there and we're going to answer it. So all eyes should be on the comment section now. All eyes should be on the comment section now. All right, so I'm about dropping the question. We're going to see it right about now. We're going to see it right about now. Okay. Okay, so let's go. I'm about dropping, let me call it Q1. That'll be the first question. So it'll be Q1. Q1. Okay. Just drop the question now. It says a 300-gram piece of metal. A 300-gram piece of metal at 100 degrees Celsius is dropped into 400 grams of water at 20 degrees Celsius. Okay, so this is a case that we just saw right about now, that a 300-gram piece of metal was dropped a 400-gram mass, a 300-gram piece of metal at 100 degrees Celsius is dropped into 400 grams of water at 20 degrees Celsius. If the final temperature is 25 degrees Celsius, we are told to calculate the specific heat capacity of the metal. We are told to calculate the specific heat capacity of the metal. All right, so let's quickly see the solution to this particular question. Like I said, this is a question under heat lost equals heat gained. Heat lost equals heat gained. Okay, so for every question as this, especially if you are taking a physics exam or a thermal physics exam, one thing you should always know is that before you start solving, identify the substance that is losing heat and identify the substance that is gaining heat. from that particular question, to get our solution, from that particular question, we see very clearly that the metal, the piece of metal, is the one that is losing heat. The piece of metal is the one that is losing it. Why? Because we were told that the temperature of the piece of metal was found to be at 100 degrees Celsius. Let me call that one theta m so that it will be very clear. Okay, so the initial temperature of the metal was given at 100 degrees Celsius. Then the 400 grams of water is at 20 degrees Celsius. So our theta W, as the initial temperature of water, was given to us at 20 degrees Celsius. So from the temperature values, we see clearly that the metal is at a higher temperature, and heat always flows from a body at a higher temperature to a lower temperature. So the metal is a body that is losing heat, while the water is a body that is gaining heat. So let's fix the other parameters. The metal, like we saw here, the metal, like we saw here, the mass of the metal, mass of metal, was given to us as 300 grams. But this is not in standard units. It's not in standard units, so I'm going to put this at 0.3 kilograms. Divide grams by 1,000 to get the equivalent in kilograms. Okay, I see a question there. Actually, I don't know what's okay. I have a doubt. Okay, go on and ask. Drop the message. Drop the message. Go on and ask. Let's clear the doubts, please. What area? Go on. Drop the question. What are you having doubts about? What area seem confusing? Please do well to drop it. I'll answer it as soon as possible. All right. Atul edits. I think so. Atul edits. Please do well to drop your area of doubt. Let's try and clear it before we proceed. Okay. I'll be waiting for you. Okay, so the mass of the metal was given to us in 300 grams, and in kilograms it is 0.3 kilograms. All right. Then the mass of water, MW. I'm going to call that MW. We have the water to be 400 grams. Yes, mass of water is 400 grams. Once again, this is not standard unit for mass. So I'm going to convert my grams to kilograms by dividing it by 1,000. To convert from grams to kilograms, you divide by 1,000. Okay? So if I divide 400 grams by 1,000, I'll get 0.4 kilograms. I'll get 0.4 what? Kilograms. Now, it went further to say that the final temperature, it means that after the metal has lost its heat to the water, it will get to a point where the metal and the water will be at the same temperature. Like I mentioned earlier, it's called the equilibrium temperature, the final temperature. That value, theta F, in this particular question is 25 degrees Celsius. This temperature belongs to both the metal and the water at thermal equilibrium, where both bodies are now at the same temperature. That's our theta F. So they went further also to mention that the specific heat capacity of water, that's the CW of water, was given to us as 4,200 joules per kilogram per Kelvin. The specific heat capacity of water was given to us as 4,200 joules per kilogram per Kelvin. At Soul Edit, I'm still waiting for your question. What areas are you having doubt? Please drop it, type it in the comments. Type it in the comments and let's get an answer for it. Or let's try and clear it up. Okay, so let's continue here. Now, we agree that the metal is the one losing it and the water is the one gaining it. So I'm going to indicate by saying if heat lost is equal to heat gained, it is going to be heat lost by metal equals heat gained by water. Okay, and we have seen before that the amount of heat a body can lose or the body can gain is equal to mc delta theta. MC delta theta, or better we say, okay, let's see that MC delta theta. All right. So for heat loss by metal, it's going to be mass of metal times the specific heat capacity of metal, okay, times delta theta for metal. That's the temperature change that the metal undergoes. And this will be equal to the mass of water times the specific heat capacity of water times the temperature change that the water undergoes. Okay? The question now says we should calculate the specific heat capacity of the metal. So we are looking for Cm. We are looking for Cm. Cm is the unknown here. The specific heat capacity of the metal. The specific heat capacity. Specific heat capacity of metal. That's what we are to look for. Okay, so we have our representation already. So let's input our values and obtain a value for Cm, which is the specific heat capacity of water. All right, so we proceed. I should be on this side of the board, please. So the mass of metal was given to us here, mm, 0.3 kilograms. So here will be 0.3 times the unknown Cm. That's what I'm looking for, times into bracket. Now, my delta theta m, which is the change that the metal undergoes. Since the metal is the one losing its initial temperature will tend to be greater than its final temperature. Okay, so because of that, I'm going to impute the initial temperature first before I put the final temperature, because it's going to be theta m minus theta f, because the initial temperature for a body losing heat is greater than the final temperature. Okay, so all of this will be equal to water. The mass of water is 0.4 times 4,200. Allow me bend here a little. Times 1 times 4,200 times into bracket. But for the body gaining heat, the final temperature is usually greater than the initial temperature. So I'm going to get theta F here, V minus theta W. That's the final temperature of the mixture minus the initial temperature of water. Okay, so let's input our values properly. 0.3 times Cm times theta m, that's 100, minus theta f, that's 25. All of this will be equal to, let me bend this down a bit. All of this will be equal to mass of water, we have already seen it before, 0.4 times 4,200 times into brackets. Theta f, the final temperature of the mixture, is 25, minus, then the initial temperature of water was given to us as 20. Okay, so all of this, 100 minus 25 should give me 75. 100 minus 25 should give me 25. All right, so this would be 0.3 times 75 cm equals, then this would be 0.4 times 4,200 times 25 minus 20. 25 minus 20 is 5. Is 5. Okay, so we're going to solve this together. Please, if you are on the call and your calculators are working, let's do this together. So 0.3 times 75. 0.3 times 75 should give us that should be 22 point something. Yes, 0.3 times 75 is 22.5 cm. 22.5 cm. This is equal to, then we'll take the right hand side, say 0.4 times 4,200 times 5. That gives us 8,400. So the specific heat capacity of the metal will be obtained from 8,400 divided by 22.5. So at the end of the day, my specific heat capacity of metal, 8,400 divided by 22.5. That should give me 373.33 joules per kilogram per Kelvin. So 8,400 divided by 22.5 will give me that value. So this divided by 22.5, 373.33 joules per kilogram per Kelvin. All right. So the metal that loses heat to the water, this is the specific heat capacity of that particular metal. This is the amount of heat that will be required to raise 1 kilogram mass of that metal by 1 Kelvin or 1 degree Celsius. I hope this is clear enough. If you understand, or if you want me to explain further how I obtain this answer, one or two things is not clear to you, please drop it in the live chat. Drop it in the live chat. Drop it in the live chat. Comment in the live chat. If this was clear enough, drop it in the live chat. I'll be waiting. I'll be waiting to give clearer explanation. Waiting to give clearer explanation. Okay, Atsulit, if you are still in the class, and I hope you are still in the class, please do well to ask your question. You mentioned that you have doubts. Please, you can drop your question in the live chat and I'll give you answers. How to edit, please go on and ask your question. Ask your question, how to edit. To let it, please ask your question. To let it ask your question. Any other person in the class, please indicate. If you're in the class, please indicate that you're in the class. And if you have questions, please also ask. This is a free class. If anything doesn't seem clear to you, please do well to ask. That's why the chat is open today. To let it. All right, so this is question 1 for today. This is the first question we'll see for today. We see that the heat that was supplied by the metal was lost to the water. That a metal at 100 degrees Celsius loses heat to water at 20 degrees Celsius until they both became 25 degrees Celsius. If the mass of the metal was given to us initially as 300 grams, which when converted to kilograms is 0.3, and the mass of water initially was given to us at 400 grams, which when converted gave us 0.4 kilograms. Specific heat capacity of water is 4,200 joules. It's 4,200 joules per kilogram. It's 4,200 joules per kilogram. 4,200 joules per kilogram. It's 4,200 joules per kilogram per Kelvin. Then we say that heat was lost. So that heat was lost to the water. All right. Now we understand that the heat quantity supplied, or the heat that can be supplied to a body or by a body, is given to us as mc delta theta. mc delta theta. So if the metal is losing heat, the mass of the metal will be times the specific heat capacity of the metal times the temperature change that the metal undergoes. The temperature change that the metal undergoes, that is delta theta m, which is equal to the mass of water, that's the body that gains it now, mass of water times the specific heat capacity of water times the temperature change that water undergoes. The question from here is that we should calculate the specific heat capacity of the metal. How do we go about that? We understand that heat loss is equal to heat gain. Last week I'm explaining again now. I explained that whenever a body is losing heat and we want to represent it, the temperature change in a question, we usually put the initial temperature first. Because for a body losing heat, the initial temperature is always greater than the final temperature. Okay, so heat, yeah, was we're looking for Cm. We have delta M, that's the initial temperature of the metal at 100 degrees Celsius. Then both of them has the final temperature 25, okay? Thermal equilibrium. All right, so 0.3 times 75, which is the difference between the temperatures experienced by the metal, and 25 minus 20, the temperature change experienced by water. So if all of this is done, Cm was obtained from 8,400 divided by 22.5. And our final answer is 373.33 joules per kilogram per Kelvin. All right. So this is question 1 for today. All right. So please, your questions are still expected. You can drop them. Let's find solution to them. Okay. So I'll be sending question 2 shortly to the chat. I'll be sending question 2 shortly to the chat. Please, let's do well to follow. This is a very high section in WAEC NECO JAMB exam. Very high. Questions like this are usually very easy, but students, they see it and they fret. They see it and they are thrown into confusion. All right, it's not supposed to be that difficult. That's why this physics clinic is holding to explain this concept step by step. Okay, so I'll be dropping the next question now. Do well to follow. If you know somebody who should be in this class, please do well to share this live with them. Do well to share this live with them. If you know somebody who should be in this class, all right. And if you have not yet subscribed to this channel, drop is do well to press the subscription button. Do well to press the subscription button. It is totally free. Subscription is totally free. Just press the subscription button so as not to miss out on any video lesson or live sections as this. Once again, the live section is open for questions. Do well to drop your questions. Okay, so we have a second question here. Almost similar to this. I think we should see it quite similar. Let's just see it to emphasize this point I've been making earlier. I think this one is for aluminium. It was pretty much specified. No. Let's see a different one. Okay. All right. So we have a different question here. This one is under electrical method. So I will drop it right now in the charts. So when you see it, we'll go through it together. All right. So let's go there. Please, let's stay in the charts and let's stay focused. Let's stay in the charts and let's stay focused. So I'm about dropping. Okay, I think I just saw a question. A 1.2 kilowatt immersion heater is used to supply energy. Adura Agbemi. Okay. A 1.2 kilowatt immersion heater is used to supply energy for 75 seconds. The energy supplied is used to heat 800 grams of paraffin in a calorimeter of heat capacity 4.2 42.5 joules per Kelvin from 20 degrees Celsius to 65 degrees Celsius. Calculate the SAC of the paraffin. That's a very nice question, all right? So before I will drop my question, Adura Bemi CD, we're going to be providing a solution to that. Please, every one person, your eyes should be on that question. Let's provide a solution to that. Okay, so let's see a solution to that particular question. All right, so like I said, we're going to break this down step by step. All right, there will be no need to rush it. There will be no need to rush it. This is a particular question on electrical method. Like we can see there, an immersion heater was mentioned. Okay, so we are going to be using the electrical method. Now, do not forget that electrical heat energy is usually given as IVT. Okay, it's given as IVT, and we also know that IV stands for power. The power of an electrical device is given as IV, which is the product of the current that flows through such device times the potential difference across it. Okay, that's the power. So it means that my heat energy can also be represented as PT. Can also be what? Represented as PT. Knowing fully well that power itself, though power has a unit of joules per second, power can also be measured in watts. Power can also be measured in what? In watts. But in that question, like I mentioned earlier, when we want to solve a question as this, I will always say, which body is losing it and which body is gaining it? You must always define, you must always ask yourself. That should be the first step you should take. Which body is losing it and which body is gaining it? From this question that was dropped by Adura Bemi, we see that it is the immersion heater that is losing heat. Okay, so the immersion heater is losing heat, so the paraffin is losing it to the what? So the paraffin, causing the paraffin to increase from 20 degrees Celsius to 66 degrees Celsius. All right, so my immersion heater is heat loss. All right, so this is going to be heat lost by heater. Heat lost by heater is equal to heat gained. Is equal to heat gained by paraffin. Equal to heat gained by paraffin. All right, heat lost by heater is equal to the heat gained by paraffin. All right, so let's quickly get the heat lost by the heater, by the immersion heater. All right, so the heat lost by the heater, I'm going to call that let's say HH. Okay, let me call it HH. HH must be equal to HP. Heat lost by heater must be equal to heat gained by paraffin. The heat that was lost by the heater is given as PT. The power times the time. Okay, the power times the time. All of this must be equal to the heat gained by paraffin. And the heat that can be gained by paraffin depends on the mass of paraffin times the specific heat capacity of paraffin times the temperature change that paraffin, times the temperature change that paraffin went through. Okay, let me remove this now. PTS stands for the heat lost by eta. MP, CP, and delta theta P stands for the heat gain by the paraffin. Okay. Now, clearly from this question, after identifying this, we'll now look forward to list out all our parameters, because in science we usually move from the known to the unknown. All right. So we are going to list out all that we know, so that it can help us obtain what we are to look for or what we are yet to know. Okay, so let's go back to the question. A 1.2 kilowatt immersion heater. Kilowatt, watt there is the unit for measurement for power. So that particular quantity is power. Power is given to us as 1.2 kilowatts. This can be written as 1,200 watts. 1.2 kilowatts is 1,200 watts. That's the value for the power. Okay, then it says it is used to supply energy for 75 seconds. Okay, so the energy supplied, or the power that was given to the water, it took a time of 75 seconds. It was supplied for 75 seconds. After all of this, it now went further to say that the energy that was supplied by the heater to the paraffin, the energy that was lost by the heater to the paraffin, it says that it is used to heat 800 grams of paraffin. So that means the mass of paraffin is given to us as 800 grams. Okay, and 800 grams, like we saw in the previous question, is equivalent to 0.8 kilograms. 800 grams is equivalent to 0.8 kilograms. All right, so if this is true, let's go further. It says this paraffin is placed in a calorimeter, all right, of heat capacity 42.5, yes, of heat capacity. So the paraffin has a specific heat capacity. I'm coming, hold on, calculate the SFC of the paraffin. Okay. All right, okay, sorry. This CP here that was mentioned is, we have another specific heat capacity of calorimeter. Okay, the specific heat capacity of calorimeter was given to us as 42.5 joules per Kelvin. So we are considering the heat also that was lost. I think I will have to change that here. Heat gained by paraffin plus heat gained by calorimeter. So it is not just the paraffin that gains heat. The calorimeter that is containing the paraffin also gains heat. All right. So this heat capacity here, this heat capacity CPCAL is for calorimeter. Okay. So let's go further. The paraffin and the calorimeter underwent the same temperature change. The paraffin, I think I should add that here. Sorry for that slip up. All right, so this will give me the next one will be CP of calorimeter times the temperature change. These two guys will have the same temperature change, so I'm going to put it as delta theta P. Okay, so this is for CPCL, that is heat capacity of calorimeter. Okay, so they underwent the same temperature change from, I'm going to call this theta P is equal to theta calorimeter. Yes, because as far they are contained in the same system. If I put paraffin inside a calorimeter, okay, I assume that the paraffin and the calorimeter, they are the same temperature. So their initial temperature in this question is 20 degrees Celsius. Then their final temperature will also be the same. Okay, so the final temperature now will now be that the heater, okay, I'm not going to consider that one. The temperature of the paraffin and the temperature of the calorimeter would have the same final temperature, theta F, both of them. So this would be 66 degrees Celsius. That's the final temperature. Both of them also have that same temperature. All right. So now let us plug in our values. We are supposed to find the C of paraffin. Find the CP, that is the C of paraffin. Let me call that paraffin PF. Okay, so specific heat capacity of paraffin. That's what we are looking for in this particular question. Okay, so let's go forward. Therefore, my PT, that's the heat loss by the heater, will be 1200 times the time is 75, and this will be equal to heat gained by the paraffin. Don't forget that I must consider the mass of paraffin. What's the mass of paraffin again? 0.8 times what next? The specific heat capacity of paraffin that we do not know, CPF. Specific heat capacity of paraffin that we are yet to know, times the temperature difference that paraffin will undergo. That will be theta F. In this case, it is 66 minus 20 plus, we now consider the calorimeter now. The calorimeter have heat capacity of 42.5. Heat capacity of 42.5. Do not forget that heat capacity is mass times specific heat capacity. All right. So this CPA is 42.5. It will also have the same temperature difference as paraffin, 66 minus 20. Okay, so let's make this smaller by punching our calculators. Please, if you are in the chat and you are following, please stay very close. Let's punch our calculators. Punch also will mean if you get your answers, drop it in the comment section. So 1200 times 75. 1200 times 75. Let's see what that will give to us. Okay, that is 90,000. So 1200 times 75 is 90,000. The heat that was supplied by the immersion heater. All of this is equal to 66 minus 20, that should be 46. Okay, 66 minus 20 is 46. So 46 times 0.8. Let's do that. 46. Oh, sorry. 46 times 0.8. That will give us 36.8 CPF. That is the specific heat capacity of paraffin, equal to, again, 66 minus 20 is 46. 46 times 42.5. 46 from here times 42.5 will give me 1,000. This is not equal to plus 1,955. Okay, so if I collect like terms here, it will be 36.8 CPF equal to 90,000 minus 1955. All right, so I want to believe you are following. Allow me to clean this part of the board. I'll try not to clean too much. Okay, so just watch this end of the board. We'll finish our solving on this end. So 90,000 minus 1955. 90,000 minus 1955 will give us 88,045. Give us 88,045. All right. So my CPF, which is the specific heat capacity of paraffin, will be equal to 88,045 divided by 36.8. So specific heat capacity of paraffin, if I divide that value by 36.8, oh, this is wrong. I think it's my calculator. 88,045 divided by 36.8. That will give us 2,392.5. 2,392.5 joules per kilogram per Kelvin. So this is the answer to that particular question, Aduragbemi. So 2392.5 joules per kilogram per Kelvin is the answer to that particular question. Does this make sense? If this is still not clear enough, let me know. This is the solution. Following through from here, down here. This is the final answer to that particular question. Is this clear enough, Adura Beni? Please indicate if this is clear enough. Indicate. If you have any other question, you can also drop it. Is this clear enough, everyone? Is this clear enough? Is this clear enough? Let me know in the comment section if this particular question we just saw now. All right. I'm glad you understood it. Thank you very much. All right. Any other question from anybody? Please do well to let me know before I drop mine now. I think the next question is something similar to this. I think Aduragbemi, you tapped into my mind. All right, so let's see this one now. I'm going to drop it now. Okay, dropped. Okay, it says a heater rated 500 watts. A heater rated 500 watts is used to heat 2 kilograms of water. Is used to heat 2 kilograms of water from 25 degrees Celsius to 100 degrees Celsius. Assuming no heat loss. When we say assuming no heat loss here, we are talking about assuming no heat was lost to the environment. It says calculate the time taken. Assuming no heat was lost to the environment, calculate the time taken. All right. So we're going to see solving this question too. Please let's stay in the class. Try not to be distracted. Let's see this one. If you have copied this or if you have jotted this down, also indicate before I clean. All right. So, okay. Okay, just in case, I will be dropping the solutions to the questions we have seen so far in our community. All right. The community can be found on this channel. All right. So I'll be dropping the solution to all of these questions we have seen today in that community so that you can always go through it, ruminate over and over. All right. So let's see the solution to the next question I just dropped. Okay, it says that a heater rated 500 watts. Okay, so we list out that parameter. Which quantity is measured in watts? That is power. So power P is equal to 500 watts. That is noted. So the next one now says is used to heat 2 kilograms of water. Oh, beautiful. So it means that the mass of water that received the heat from the heater is 2 kilograms. Noted. Now, what happens after that heat was supplied by the heater? We saw that the temperature of the water moved from an initial temperature θ1 of 25 degrees Celsius to a final or new temperature of 100 degrees Celsius. Now the question is, calculate the time taken. How long did the heater supply the heat? Okay, assuming no heat was lost to the environment. Remember, for heat loss equals heat gain, it must be happening in a conserved system. The system must be conserved. All right, and for us to have a conserved system, it means that there is no external factor acting. Okay, there's no external factor, there's no heat added from outside, there is no heat lost to the outside. So we are considering the system of the heater and the water only. Okay, so it was not lost to the environment. Calculate the time taken. How long did the heater supply that amount of heat? Okay, so the heater is the one losing heat here. Once again, heat lost is equal to heat gained. Heat lost is equal to heat gained. The heat lost by the heater, like we saw earlier in our previous question, the heat that is lost by an electrical heater is given as PT, that's power times time, or IVT, or I squared RT, okay, or VV squared R over T, whichever one, okay. But in this particular question, we're going to consider PT. All right. So the heat lost by the heater was gained by the water, and the heat that is gained by water is given as the mass of water times specific heat capacity of water times the temperature change that water underwent. Do not forget that by now we should know that CW, that's the specific heat capacity of water, is 4,200 joules per kilogram per Kelvin. That's a constant value for the specific heat capacity of water. By now we should know that, right? So quickly, power was given, mass of water was given, specific heat capacity of water is a constant, it is known. All right. Then the temperature change that the water undergoes was also stated from theta 1 to theta 2. So what am I looking for? I'm looking for the time. How long did the heater supply this amount of heat? So if I make time my subject formula, time will be equal to mw cw into the brackets. This will be theta 2 minus theta 1 because it is the water that gained. So to be theta 2 minus theta 1 over the power. Okay, so I think we have done almost all that we need to do. I think we have done all that we need to do here, just for us to put in our values, just for us to slot in our values and obtain the time through which the heater supply that amount of heat. So the mass of water is 2 kilograms. The specific heat capacity of water is 4,200 joules per kilogram per Kelvin. And the temperature change, theta 2 is 100, theta 1 is 25, then our power is given to us as 500. So we are going to slot all of that in and obtain our answer. So let's see. Sorry, like I said, I'm going to drop the solution to all of this in the community. So do well to expect it in the community. All right. So my time, therefore, mass of water 2 times the specific heat capacity of water 4,200 times theta 2, that is 100, minus theta 1, that is 25. This will be divided by the power, that is 500. Okay, so if I do this, this will be 2 times 42 times 75 over 5. I know you are wondering what just happened. Well, these two zeros here, we cancel these two zeros. That's what just happened. All right. So these two zeros that stands with 500, I'll use them to cancel this 2 zero that stands with 4,200. So I'm left with just 42 here and 5 here. And 100 minus 25 is 75. Okay, so we proceed. Time t would therefore be equal to 2 times 42, that will be 84. So we have 84 times 75. That is 6,300. 6,300 divided by 5. So the total time through which the heater supplied the heat will be given to us as 6,300 divided by 5. That is 1,260 seconds. 1,260 seconds. It means that the heater was on for 1,260 seconds. It is through this time that it was able to supply the amount of heat that was gained by the water that causes the water to rise from 25 down to 100. Okay, so this is another solution, another beautiful solution. All right, like I said, questions under specific heat capacity and the rest heat measurement, it is usually very easy if you understand it to this level, as basic as this. Always identify the board that is losing heat and identify the board that is gaining heat, knowing that first of all you are halfway done. Okay, knowing that first of all you are halfway done, and your other things, MC delta theta, do not forget that also, very important. All right, so if this was clear enough, also let me know, indicate that this was clear. If there's a gray area that is not clear, if there's a gray area that is not clear, please also let me know. Also, let's find a solution to it. All right, thank you, Bolu. Thank you very much. Thank you for that, Bolu. All right, so if you have any question, please do well to drop it. Do well to drop it. I'll be here to answer. I'll be here to provide answers to your questions. If you have a question, ask. I'm glad we all are following. I'm glad we are following. Do not shy away, we'll ask. I'm here to answer. We'll provide a solution. We'll provide a solution no matter. Remember, it's a physics clinic. What do we do in a clinic? We treat people, right? So in this clinic, we treat and provide solutions to physics problems, no matter the shape and form they take. We provide the solution. Please, I want all of us to be very active. I want us all to be very active. Do not just be a passerby. Actively, let's be active on the charts. Okay. All right, this is another one again. Adura Bemi. Okay. The temperature of water from tap A and B are 25 degrees Celsius and 75 degrees Celsius respectively. What's happening? Okay. 25 degrees Celsius and 75 degrees Celsius respectively. Okay, if a mixture of water at 40 degrees Celsius is required, calculate the ratio of the mass of water from tap A to that from tap B. Another very good question. We're going to provide a solution to it right now. Okay, so let's proceed. That's a very nice question. All right, so let's see. I want to believe we have taken this down. All right, so I want to solve this particular question that was dropped by Benny. So let's see. Okay. Yeah, there's a reason I have left this guy here ever since. I just do not want to clean it. It's lost equals gain. Let it remain here for as long as possible. Okay, so let's see the solution to this. Like I said, in science, we move from the known to the unknown. It's always from the known to the unknown, right? So what is known and what are we to look for? Let's start with that. What is it that is known? the temperature of water from tap A. So it means we have two taps, okay? From tap A and tap B are 25 degrees Celsius and 75 degrees Celsius respectively. So temperature of water from tap A, theta A, is given to us as 25 degrees Celsius. Okay? And the temperature of water from tap B, that's theta B, was given to us as 75 degrees Celsius. Now, it says if a mixture of water, okay, that's another question again, nice one. If a mixture of water at 40 degrees Celsius is required, okay, if we are requiring that at the end of the day, the temperature of the water should be 40 degrees Celsius, it means that the final temperature of the water after mixing water from tap A to with water from tap B, I'm expected to have a particular temperature at the end of the day. If what I'm expecting is 40 degrees Celsius, it means that that is the final temperature. 40 degrees Celsius is the what? Final temperature. Are we together? So the question now says, calculate the ratio of the mass of water from tap A to that from tap B. So we are told to look for um, to look for mass of water of tap A to mass of water in tap B. Something like saying MA ratio MB. This is what we are told to look for. Alright? The one thing that we must also note is that this two bodies being considered here, they are both water. So they will have the same specific heat capacity. Alright? They will have the same specific heat capacity. Alright? So let's quickly delve in. Alright? So between tap A and tap B, which one do you think will lose heat? Between tap A and tap B, which one do you think will lose heat? Tap A was at 25 degrees Celsius. Tap B was at 75 degrees Celsius. So because tap B is at a higher temperature, it will lose its heat to tap A. So heat is being lost by tap B and heat is being gained by tap A. Alright? So what this means is that heat lost is from tap B, while the heat gained is from tap A. Heat loss is from tap B, while heat gain is from tap A. So what is my heat gain by tap B? It's going to be the mass of tap B times the specific heat capacity of tap B times the temperature change that tap B went through, delta theta B. All of this will be equal to mass of water from tap A times specific heat capacity of water from tap A times the temperature change that tap A undergoes. Alright, so let's proceed. Mass of B, okay, let's hold on somewhere. I said that specific heat capacity, the specific heat capacity of water is the same whether it's tap A or tap B. So my CB is equal to CA. Alright, so this will likely cancel out at the end of the day. So I'm going to get mass of B, CB times, here's what I'm going to now work on now. Delta TB is the one losing heat. TB is losing heat. That's tap from water from tap B is the one losing heat. So what's the initial temperature? 75, right? So this is going to be theta B minus the final temperature, theta F, equal to mass of A. Now, since my CB is equal to CA, because they are both water, here will be CB, then times tap A is the one gaining heat. Therefore, my theta F will be greater than theta A. Now let's slot in our values. CB, we cancel CB. So MB, so I'm going to get MB into bracket. Theta B is 75 minus theta F is 40 equal to MA. Theta F is 40. Theta A is 25. 75 minus 40. That should give me 30 there. No, that would give me 35. 35. So here will be 35 MB equal to 40 minus 25. That should give me 15 thereabouts. Yes, 15. All right. So this is 15 MA. Are you following? This will give me 15 MA. All right. So if this is true, what am I looking for? And I'm told to find the ratio of the water in tap A, the ratio of the mass of water in tap A to the ratio of the mass of water in tap B. So I'm looking for MA over MB. Let me represent MA over MB here. If I do that, I'm going to get 35 over 15 equal to MA over MB. So what can go through here? At the end of the day, I will have that my MA is equal to my MA over MB is equal to 5 here is 3, 5 here is 7. So it's going to be 7 over 3. So the ratio is 7:3. There's the correct answer to that question. Right? So the ratio of water in tap A, the ratio of the mass of water in tap A to the ratio of the mass of water in tap B is giving us 7/3 or 7:3. Solution provided. Once again, step by step. There's no need to rush it. Step by step. Does that answer you? Does that answer you? Demi? Do you understand? Please, if you comprehend, if you're on the call and you comprehend this particular solution, please indicate. If you understand this particular solution, please indicate. Please indicate. I think I have 2 more questions. You have 2 more to solve before this class will come to an end. All right, well understood. Well understood. Every other person understand, right? Every other person understand, right? Let me get a confirmation before I proceed. Okay. All right. All right. So let's solve the last 2 questions before we call it a day today. Please, if you are on this call, this is Physics with Polami, and today we are observing our physics clinic where we look to provide solutions to difficult physics questions. Not just that, anyways, where we also look forward to explain questions that that to look forward to explain concepts that seems to be very tricky, especially in examination conditions. All right. So let's solve the last 2 questions for today, and we'll call it a day. Okay, Bolu, you dropped a question. An electric heater connected to a 240 volt supply draws a current of 5 amps. Okay, it eats 2 kilograms of water for 8 minutes. Calculate the heat energy supply. All right, so that's a pretty much direct question. I'm coming to that later. I think David, a 500-gram block of copper is heated from 20 degrees Celsius to 80 degrees Celsius. If the specific heat capacity of copper is 0.385 joules per gram per degree Celsius, calculate the amount of heat energy transferred to the copper block. All right, beautiful. That's another nice question. So we'll end with these two questions for today. We end with these two questions for today. I really hope we are able to cover latent heat. So we're having it for part 3 as well. All right, so that part 3 may come up during the week, anyways, so that on Sunday we can proceed to other topics. So let's see. Let's solve these last two questions. Let's solve these last two questions. All right. So once again, to solve any kind of question, you must first of all list out the quantity that was given. So let's start by listing out all the quantities. It says an electric heater connected to a 240 volt supply. Okay, that 240 volt supply has a potential difference of 240 volts. That's what it means. Okay, and the supply draws a current of 5 amps. So a current of 5 amps was drawn by that supply. All right, and yes, full stop. It says this particular supply eats a 2 kilogram of water. So the mass of water that was heated is 2 kilograms for 8 minutes. So the time that eating took place lasted for 8 minutes. Then you know that minutes is not the standard, so I'm going to multiply 8 by 60. 60 seconds make 1 minute, so this will be 8 times 60. That should give me, I think if I'm not mistaken, that should be 480. That is 480 seconds. We have 480 seconds. 480 seconds, yes. 480 seconds. 480 seconds in 8 minutes. Then we proceed. It says calculate the heat energy supplied. Calculate the heat energy supplied to the water. Okay, so this is a simply direct question. What is supplying this heat? What is losing this heat to the water? It is the electrical heater. And the electrical heater is an electrical device that supplies electric energy. So you are simply told to find the electrical heat energy. That's what they are simply telling you to look for. And the electrical heat energy is given as IVT or PT or I squared RT. Not just that too, or V squared R. Sorry, V squared. This is V squared over. No, I'm not making a mistake. Okay, I think this is alright. So I squared RT. But in this particular question, the heat energy, we have the current given, that's the current I. We have the potential difference given, that is V, and we have the time given, that is T. So the heat supply to the water is simply 5 times 240 times 480. So heat energy will be equal to, if you have your calculators, let's do some punching. 5 times 240 times 480. That will give us 576,000 joules. 576,000 joules, or putting this in kilojoules, it will be 576 kilojoules. 576 kilojoules. So this is the amount of heat energy that was supplied to the water, and it was supplied by the electrical heater. So let me get responses. Is this question well understood? Is this question well understood? Please, if you understand, indicate. Indicate. Was this question well understood? If you do, please indicate. Indicate in the live chat that it's well understood. It's well understood, please indicate. Crystal clear. All right. Crystal clear. Beautiful. Okay, so let's see the last question for today. Let's see the last question for today. Now, please, this section may end, but this is not the end. If there is any other question you find or you come across while you are doing your personal study, whether you are a student on this chat currently or you come across this particular video, this live video during the course of the week, my community is open. My community is open on this channel. Do well to drop the question. If you have any other questions at all as relating to physics, you can always drop it in that community, and solutions and explanations will be given in the subsequent physics clinic, or better still, in our subsequent video lessons. All right, so even at the end of this class, you can still drop your questions and they will be duly attended to. So let's see the last question for today. Let's see the last question for today before we call it a day. All right, so let's go. Okay, let me clean this side now. Oh, I've cleaned my ink. So, solution for our last question for today. Solution for our last question for today. Okay. Okay, it says a 500-gram block of copper. Right? So that means the mass of copper, MCU, is 500 grams. And this is given in terms of grams, right? So we have to convert to, I think, okay, no, let's leave it in terms of grams. Come here, yes. Let's leave it in terms of grams, all right? Since the specific heat capacity of copper was given in terms of grams, all right, and the mass also in terms of grams, there will be no need here converting, okay? There will be no need here converting. This is one thing I usually say. Before you start to even convert, always check for if there is a constant in that particular question, all right? If your constant is in the unit of a particular quantity mentioned, you leave it like that, all right? As you can see here, the specific heat capacity of copper is given as joules per gram, okay? And the mass is given in terms of grams also. So we'll just proceed like that, all right? So the mass of copper is 500. Then, okay, this copper was raised from an initial temperature. When the heat was applied, it moved from 20 degrees Celsius to a new temperature of 80 degrees Celsius. When the copper was heated, it moved from 20 degrees Celsius to 80 degrees Celsius. The specific heat capacity of copper, that is my CCU now, is given to me in this question as 0.385 joules per gram per degree Celsius. Alright, and we are told to calculate the amount of heat energy transferred to the copper block. The amount of heat energy transferred to the copper block is simply the heat quantity of the copper block. And we know the formula very well, MC delta theta. Okay, so this is the amount of heat energy transferred to the copper block. So let's get the value. H should be equal to the mass of copper is 500 times the specific heat capacity of copper is 0.385 times what temperature change did it undergo from theta 1 to theta 2. So this will be theta 2 minus theta 1. So it will be 80 minus 20. So 500 times 0.385 times 60. So let's do that mathematics. Punch your calculators with me. So I have 500 times 0.385 times 60. So the heat energy is giving us 11,550 joules. 11,550 joules, or if I convert this to kilojoules, it will be 11.55 11.55 kilojoules. So this is the heat energy that was supplied to the copper when its temperature moved from theta 1 to, sorry, from 20 degrees Celsius to 80 degrees Celsius. All right, so this is the beautiful solution to that particular question. So once again, if this particular solution was clear, indicate in the live chart that you understand, indicate in the live chart that it is well understood, that it is well understood. If not, please let me know so that I can give further explanation. Let me know in the chat, please. And let me know in the chat before we conclude so ninth section. Let me know in the chat. Really, Dr. Polamin. Thank you, thank you. All right. Any other person in the chat? Is this clear enough? Indicate that it is clear enough. If you need further explanations, also indicate. All right. Okay, so we'll be having a class midweek. Also live here. I don't know the particular dates right now, so that we can finish up everything on its measurements. Hopefully, I will not want us to carry this over to next week. All right, so we're likely going to have a class midweek. What we're going to finish up its measurements. We're going to talking about latent heat. Latent heat. That's like the last part of everything that has to do with heat measurement. Okay, so I will just give a brief introduction right now, even as we wrap up. I'll give a introduction, then during the course of the week, we'll have a live class where I will explain further and we'll see questions under it. So I will explain further, then we'll solve some questions under it also. All right, so in the absence of no other question for now, like I said earlier, you can drop your questions in the community on this channel. Drop your questions as relating to this, even as relating to other physics questions. You can drop it in the community, and solutions will be provided in due time. And then again, our physics clinic continues weekly, every Sunday 4 o'clock p.m. Every Sunday by 4 o'clock, we'll meet to talk about physics. We'll meet to provide solutions to difficult concepts, to provide solutions to difficult questions as it borders around physics. Okay, especially those high topics like thermal energy, thermal physics, mechanics, talking about light and optics, electricity. All right, we'll be tackling all of those live here on this channel. Okay, so if you have not subscribed, here's my call again. Do well to press the subscribe button and be a part of our live section so that you don't get to miss out on anything. Yes, that you don't get to miss out on anything. Trust me, the value here is so much that you don't want to miss a thing. Okay, so stay subscribed so that whenever we drop a video lesson or whenever we'll be having a live section, you'll be the first to get notified. You'll be the first to get the ring bell that yes, something is about to go down. There is actually value here. I don't know how I'm going to say it, okay, but there's so much value on this particular channel, physics with Polamin. If you have not subscribed again, press the subscribe button. I know what I'm saying. Just press it. It's free, just okay. And if you know somebody that would need these sections, somebody taking WAEC exams in a couple of months, JAMB exam is coming up in some few days. I think it's 30 something days to JAMB already. You know somebody who will be taking WAEC on the GC, all right? Or somebody in the beginner classes like SS1, sorry, grade 10, grade 11, and grade 12. Or somebody preparing for post UTME. This is one channel that they should be a part of. This is one channel that they should be a part of. So let them know about it. All right. So in the next 7 minutes, I'll just lay a foundation on latent heat, and that will be it for today. All right. So when materials actually change state, when a material from, let's say, a ice block change from ice water to liquid water, from ice water to liquid water, when that change occurs, it occurs usually at a constant and definite temperature. Okay, when there's a transition from ice to liquid, it occurs at a constant and definite temperature. It means that when ice is melting to liquid, temperature is not increased. We are told that the melting temperature for water is 0 degrees Celsius. Okay. So as that ice is melting, the temperature does not increase until the ice has totally melted. Before the temperature will start to increase from 0 to 1 to 2 to 3. Okay, but as far as the melting process is still going on, the temperature of that liquid, of that water, is not going to increase. It will remain at 0 degrees Celsius. Okay, but then you now ask yourself, why then am I observing a change of state? Why then is still a change of state? Why am I still having a change of state? I thought it is needed for change of state. Yes, it is needed for change of state, but that is somewhat hidden. Its effects or its value is somewhat hidden. That's why it's called latent heat. Something hidden. Something hidden. So that heat that results in change of state at a constant temperature is what is called latent heat. All right. So when a substance transits from solid to liquid, it requires latent heat. When a substance transits from liquid to steam or vapor, it requires latent heat. The conversion of the heat that is required for the conversion of ice to liquid, that particular heat or latent heat is called the latent heat of fusion. The latent heat of fusion, all right, where an amount of heat is required to transit a substance from its solid state to its liquid state. It's called the latent heat of fusion. Okay, then when we consider a state where liquid transits from that liquid state, a substance transits from its liquid state to vapor or to steam to its gaseous state, such a process or such amount of heat or the heat that is required for such transition is called the latent heat of vaporization. So all of this, we are going to be talking about it on this channel during the course of the week. Like I said earlier, I do not want to carry this to next week Sunday. So stay posted. Stay posted. You will get a notification for when this class we hold during the course of the week. All right. So get yourself prepared. Get yourself prepared. If there are further questions you want to ask, like I said, you can still drop them on the comments, or better still, drop them in the community, and you will get your answers. Okay. So we have come to the end of today's live section. I'm glad that you stayed true. It's been close to 2 hours of amazing conversations, amazing discussions. I'm glad that you stayed true to this point, and I'm rooting for you as regards your reason for being here, whether you're preparing for an exam or you just want to get yourself grounded in the concept of physics. I'm rooting for you. I'm saying success to you in that endeavor. All right. So before I leave, my name is Paul. You are calling me Paulami, and this is Physics with Paulami. So I'm urging you, get notified. Every Sunday by 4 o'clock, we meet on this channel to discuss everything physics. Okay, so always drop a like, always share this particular channel, and always comment when you need to comment. We have videos from last year that covered some part of physics. You can as well go back and just binge on those videos, go through those videos. There are lots of value there. There are lots of value. Go through those videos, like them, not just like them anyways. You can also drop a comment of one or two things you do not understand, and trust me, I'm going to treat that in our physics clinic if you do that and if you bring my attention to those things. Thank you very much for being a part of this particular section. You are the real MVP, and I'm happy to be here sharing what I know, to be a part of your academic journey. All right? So, yes, Paul saying, hi, have a great evening. All right, so we call it a day. You guys go enjoy. Go enjoy, please. Let's keep reading. Let's keep reading and studying. Let's keep reading and studying. It's going to be a beautiful one for us. All right, so if you see these charts here on this app, if you see this video lesson here on this app, do not forget it is filled with so much value. It is filled with so much value. It is filled with so much value. All right, so much value. Thank you very much, and God bless you.